Hello everybody, my name is Aujin and welcome to Lab Report 2, Lines of Charge for Physics 2212. Here's the table of contents. So the goal/purpose is to find the estimate or magnitude of the charge on one piece of tape in which it is necessary to float one tape above the other, which is based on the calculations from the computational model, in which you're also creating a simulation to model the charge on the tapes. Assumptions is to ignore air resistance on a moving object, and each U-tape made has the same amount of charge evenly distributed. To treat the tape as static such no motion, and also the tapes are rigid and thin lines. Some errors that may or may not occur, some inaccuracies when measuring distance between tapes. Concepts as fundamental principles is the conservation of charge, Coulomb's law, electric force, electric field, and superposition principle. The preview of the lab results that at 0.16 meter tape has a rough estimate charge of roughly 3.20 e to negative 8 coulombs, which is needed to move the bottom tape due to the top tape. The top tape was positively charged. The method here is to place the tape on the table, then another piece of tape on top, separate, then place one tape on two objects, then using the other tape here in blue, we then find the distance at which this blue tape affects the red tape. In this case, for our experiment, we actually have the blue tape here on the top. And note that the charges are opposite. Computational model, the length of a tape was 0.16 meters, the mass was 1.6 e to the negative 4 kilograms, and the distance between them in which it was starts to be affected was 0.05 meters. Here for the computational model, we have our constants in mass, which is 1.6 e to the negative 4 kilograms, charge, which will be discussed later on. And here we're defining our electric fields, which is our magnitude, r hat, which is r divided by r mag, and the electric field, which is K times charge particle dot charge divided by the r magnitude squared times r hat. Here we're defining, we're also helping define dq, which is going to help us later in the future. Q, which is Q is equal to Q over N. This will help us find like the magnitude of each point charge. And this is the link to my glow script. Here we have the top tape and bottom tape. These just represent the positions of them. We have the scalars for the electric field, the electric force, and gravitational force. And here, this is the most important part. This represents the integral of dE. This is our overall dE. So that each point, we're just taking each point and taking the overall integral. The overall integral would just be the integral of k times dq over r squared times r hat, and this is what it's represented by. Here we just have what we're going to be representing in our final observation. We have the arrow for the electric force and gravitational force, and here we're just printing out the magnitude, electric force on bottom, and the gravitational force, and here we also have our codes. For results test observations, the estimate charge, magnitude in which the bottom tape was affected by the top tape was 3.20 e to negative 8 coulombs. This is shown because the magnitude of electric force at that charge was 1.577 e to negative 3, which is greater than their gravitational force here. And this is the top tape represented by red. This is the bottom tape represented by blue. The white arrow is the electric force. The yellow arrow is the gravitational force. And the green arrows are the electric field. Now, what if I had modeled each of your tapes as a single point charge and compare the estimate value of the charge you get when you use your experimental data to produce a point charge model to the value you got with your line charge model. From the previous experimental model, our charge would be 2.1 e to the negative 8 coulombs, but now compared to before, it's 3.20 e to the negative 8 coulombs. Why do these estimates differ, and which value is more likely to be closer to the real value, and why? The 3.20 e to the negative 8 coulombs is more likely to be closer because the line charge model is more accurate for long objects because it accounts for a distance variation along the tape, while a point charge approximate is simpler, but it ignores geometry, thus less accurate. So conclusion is that the computational model was accurate, and at 0.16 meters, the tape has a rough magnitude charge of roughly 3.20 e to negative 8 coulombs, and which is required to move the bottom tape due to the top tape. And thank you for watching.